Hey everybody, Dr. Retzek here. This is our first video in section 16.3. You'll see on our reading schedule 16.3 and 16.4 are 3 days each. There are some technicalities between us and the beauty and utility of 16.3 and 16.4, so we really want to take our time and make sure that we have the sequence of ideas all organized. Let's get started. So 16.3 is about what are called conservative vector fields. I've taken the liberty here of drawing a bunch of arrows to represent a vector field. And we want to think about paths connecting these 2 points, say point A and point B. Now, there are all sorts of paths that might connect those 2 points. There's this sort of reasonable looking path like that. There's this path. There's really all sorts of different paths that we might take to get from A to B. The question becomes, how does the line integral of the vector field depend on the path we take? If it doesn't depend, then we're dealing with a very special type of vector field. Okay, so if the value of the line integral of f dot dr depends only on the initial and terminal points of C, so not on the path itself, we say the line integral f dot dr is independent of path. So that's vocabulary right there, independent of path. And f is conservative. So those are the first 2 words that we want in our lexicon. Independence of path and conservative vector fields. Now, the vector field we're all sitting in at this moment, Earth's gravitational field, is conservative. And I remember growing up, I lived on a pretty steep hill, and actually I live at the top of a steep hill right now too. But I remember when I was a kid, I lived on Carolina Street, and it was really steep, and it was great fun to ride our bikes down to the bottom where it flattened out. But riding back up to the house was less fun, and I remember having to zigzag back and forth because the hill was so steep. And I remember thinking to myself, oh man, I mean, this helps me get my bike all the way back to the driveway, but this is taking forever, all the zigzagging. You know, and then maybe some grown-up on a 10-speed just goes straight up the hill. And I think, oh, that's the life. Look how much less work it is for that guy than it is for me. Well, in fact, it's the exact same amount of work. It doesn't matter whether you take a straight route up to my driveway or you zigzag back and forth. one way or another, the total amount of work you do is the same. And it's because Earth's gravitational field is conservative. So it's independent of path. The path to my driveway, it doesn't matter. Okay, so in principle, now we know what a conservative vector field is. It's one in which the values of these line integrals don't depend on the paths, only on the starting and ending points. Okay, that's great. Now, some vector fields are particularly friendly. Definition. If you have a vector field big F that just happens to be some function's gradient, then big F is called a gradient vector field. And little f is called its potential function, or sometimes for short, its potential. Okay, so let's look at an example. So let's start with a function little f. Let little f of x, y, z be xy squared plus y sine z. That's a perfectly reasonable function of 3 variables in a chapter 14 sense. Then the gradient of that function little f is the vector with the partial derivatives in each entry. So first entry is partial df dx, which is just y squared. Second entry is, let's see, partial with respect to y, so 2xy plus sine z. And third entry is partial with respect to z, so y cos z. Okay, so that's the gradient. Nothing new there. We've been computing gradients all the way since chapter 14. Okay. So big F, defined on 3D space by y squared 2xy plus sine z y cos z is a gradient vector field with potential function little f of xyz equals, what was it? xy squared plus y sine z. Fantastic. So if someone hands us a function little f, we can just find its gradient, and then we will have in our hands a gradient vector field, and we'll know the potential function because it's the function we started with. Okay, that's great. Now, let your mind wander a little bit and think about problems where you don't know little f in advance. Is big F of xyz equal to xyz z e to the xy squared, and then tan inverse of yz a gradient vector field. Okay, so if someone asks you that question, they're asking you, hey, is this big F really just some little f's gradient? And you look at it and you start thinking kind of like, well, maybe. I mean, maybe we could dream up. Is it possible? Is it even possible? Could this be df dx and this df dy and this df dz if we were super clever and came up with just the right function little f? Is that possible? And I guess at a glance, I mean, like, I look at it and it looks daunting, and I kind of think, oh, the three entries look way too different. I don't see there being a little f that could do this. But that's all instinct. I mean, I don't really know. I guess you would have to get in there and see, try to find a little f. Anyway, it's a real question. Definitely, it seems like a legit question. And even if you could answer it, is that an answer like, yeah, there's definitely a little f, but I can't tell you what it is? Or, yeah, there's definitely a little f, here's what it is. So this is a real question, and it's part of what we're trying to figure out here in section 16.3. Okay. If you knew, though, that you had a gradient vector field, then it turns out line integrals of that vector field are much, much simpler than it seemed they might be back in 16.2. Okay. This is called, the fundamental theorem of line integrals. This is a big one, and this is a really important one to have in your bag because it's going to take problems that were hard and make them much easier. Here's what I propose. I'm going to write down the conclusion, and then we'll talk about all the different hypotheses. Okay, so conclusion first. Here's the conclusion. If you have a curve like this, and it goes from some point A to some point B, traced out in that direction, call that curve C if you like. If you are interested in computing the integral over C, f dot dr, if you knew that f was somebody's gradient, if it turned out that you were so fortunate that the vector field in question was somebody's gradient, then computing the line integral, don't parametrize the curve. Don't do out some dot product. Don't do all those integrals with t's in it. Don't. If f is a gradient vector field, then all you have to do to evaluate the line integral is stick b into the potential function. That's the ending point. Stick a into the potential function. That's the starting point, and subtract. It's a good old-fashioned fundamental theorem of calc looking result. So this box right here, this blue box right here is gold. it takes this process from 16.2 where we have to parametrize and integrate stuff with tsnet and just turns it into, nope, find the potential function, evaluate at the endpoints, done. Now, I mean, I sound a little flippant about that. I make it sound like, yeah, just find the potential function. But all right, maybe finding little f is not that easy. But man, if you knew in advance that there was a little f, all you would need to do is evaluate it at the endpoints. All right, let's talk hypotheses here. There are some technicalities. So we're going to end the video with the hypotheses. Hypotheses for fundamental theorem of line integrals. Okay, we're talking about a smooth curve. All right, the curve has to be smooth. Okay. Second hypothesis. You guys remember smooth means the derivative's never zero. Okay, second hypothesis. We got to be talking about some sort of domain that contains the curve. So, what color? Green. Green for go. This is all happening inside some domain D on which the vector field big F, which is equal to the gradient of little f, is continuous. So the gradient little f is continuous on D. Now, within that second hypothesis, you need a few things to be true about D. D needs to be an open set. Remember, open meant each point in D has an entire circle around it in D. In other words, D doesn't include any of its boundary points. Every point of D is interior. Okay. We also need D to be connected. Connected means any 2 points in D have a path between them that doesn't leave D. Finally, D is simply connected. Simply connected means any closed loop inside D can be shrunk to a point like a shrinking rubber band without leaving D. Now, intuitively, what you're saying there with simple connectedness is that D has no holes. Because if D had a hole, so imagine D was like this instead. If D is this region, so it's the gray, and that hole in the middle is missing, then you can see this loop in D, it's impossible to shrink it to a point without leaving D. So this is not simply connected. Although it is connected, look back at that picture. If we're calling this D, true or false? Just use your eyes. True or false? Is it the case that any two dots in D can be connected by some path that doesn't leave D? I think the answer is yes. It's fine. Just go around the hole. You can get from this dot to this dot with a path. Just go like this. So any two dots can be connected with a path, but there are certain loops that can't be shrunk to a point without leaving the set. Now, truth be told, the definition we're giving here for the word connected, I think technically is the definition of the math vocabulary word path connected. And connected and path connected are not legitimately synonyms. For our purposes, think of connectedness as path connectedness. Okay, so those are all lurking in the background, all those hypotheses. Try not to let the hypotheses cloud the beauty of the blue box. The blue box is where it's at. If you are so lucky to have a vector field that is somebody's gradient, then the line integral is easy. Just evaluate the potential function at the endpoints and subtract, just like you would on any old integral. Evaluate at the endpoints and subtract. Okay, you guys are going to read up through the two questions on page 925 of Thomas and come to class with questions so that we can start practicing some problems involving gradient vector fields, potential functions, and the fundamental theorem. Okay, I'll see you next time. Bye.